Okay guys, here we go. What we're going to be looking at today are techniques, different techniques that we can use to actually fit these to one of the rules that we already know. So we've used some of these before. If you'll take a look at here, the expanding, we've done that before, where you multiply things out so that you can handle them one by one. We've done a little bit of this, separating the numerator. So this expression, pretty hard. This expression right here, pretty hard to integrate. But if we split it up, this one, hopefully you recognize that as arctangent. And then this one, we could use U substitution on. So that is a technique that's a pretty good thing that we can do. Complete the square. We worked on this before the break. If you remember, we worked on completing the square. If we could get this to be, 1 minus or a constant minus x squared, then it looks like arcsine. We can work with arcsine here. Now this one right here, the dividing one, we don't have very much experience with. We'll do one in the notes today. If I have an improper rational function, in other words, if the power in the numerator and the denominator is the same or the numerator is higher, then I can actually divide it. I can use long division and I can divide it out so that I have the whole part, which is usually pretty easy to integrate, and then the fraction that's left over. This looks like, arctangent, so we could use arctangent here. So that's a pretty handy technique, is dividing. That one we haven't really worked with much at all. On this next one, adding and subtracting terms in the numerator. As it is, this one really, if I do a U substitution with the denominator being U, I would get, my derivative would be 2x plus 2. Well, I don't have a 2x plus 2 in the numerator. I only have a 2x. So what you can do is you can add 2 and subtract 2 so that, you're not really changing the value because you're adding 2 and subtracting 2. And what you get, then you split the fraction. This first one we could do with the U substitution. And the denominator is actually factorable, so this looks like a fairly easy U substitution as well. So that would, as a technique that we haven't done very much, we'll do some in the notes where we add and subtract terms in the numerator. Trig identities, we've worked on those before, should be pretty comfortable with that. This last one, multiply and divide by a Pythagorean conjugate. For this one, we're attempting to change the way it looks so that we can use some Pythag to rewrite, because as it is, this is not going to be able to be integrated. So if we multiply by the conjugate, you'll see here we get 1 minus sine squared, which we should all know is cosine squared. And then we can split this, and we would be able to integrate this part. So it's kind of just pulling together all the things that we've learned before in a different kind of package, just showing us different algebraic things that we could do to break this apart. Okay, questions so far? We okay? All right, we have a few examples. We have 4 examples to work. So let's practice some of these. If you are looking on the syllabus, I actually I just changed up a little bit. If you're paying attention to the topics, we're only going to do 1 day on trig integrals instead of 2. And I'm taking this as one of the trig integral days because I think this lesson is pretty important. We just need to pull it all together instead of just assuming that we all know exactly what to do. So that's what I've done here. Let's take a look at our first one. If we try to do U substitution, that's really not going to work very well for us. It's possible we might be able to do like a double U substitution. But instead of going that route, let's think of one of the new techniques that we've learned. These x squareds right here in the numerator and denominator, that's an improper rational function. So let's do long division. Let's try to rewrite this by doing long division, remembering that the numerator goes inside the box and the denominator on the outside. So x squared goes into 4x squared 4 times. So then we multiply back out. 4x squared, 4 times 9 is 36. I subtract. I get a negative 36. So basically what we have is, I can rewrite this integral. Move this out of the way. Okay, we can rewrite this integral to be the integral of 4 minus 36 over x squared plus 9 dx. So this 4, pretty easy to integrate. We know how to integrate the 4. This 36 over x squared plus 9 looks kind of like arctangent to me, doesn't it to y'all? It's kind of, so we can use arctangent here. So let's do that. I'm going to go ahead and rewrite it as two integrals. You don't really have to, but just to be clear what we're doing. So we have basically integral of 4 dx minus 36 times the integral of 1 over x squared plus 3 squared dx. Okay, so we get the, for the first integral, we get a 4x and then minus the 36. So let's think about our formula. Since this x has a 1, the coefficient is 1, the x squared is, the formula for arctangent should be pretty easy. We just have to remember what it is. Now, if you'll recall, 2 of the 3 formulas need to be multiplied by 1 over a. Remember in front? Is this one of the 2 formulas that needs to be multiplied by 1 over a? It is. It is, isn't it? So a in this case is 3. So we're going to multiply by 1 over 3. And then we have arctangent of, remember it's u over a, or in this case x over 3 plus c. So cleaning that up, we get 4x minus 12 arctan x over 3 plus c. Okay? Is that one okay? Any questions? Okay, let's take a look at the second one. The denominator looks quite a bit like arcsine, doesn't it? But in the numerator I have the x plus 3. That's not going to, I can't just do a regular u substitution, because if I set this equal to u, I'm not going to get x plus 3. I mean, that's just not going to happen. So we have a couple of options here. Probably one option would be to split this apart into 2 fractions. And so let's do that. And again, the x over the radical 4 minus x squared, and then plus, let's see, 3 over radical 4 minus x squared dx. So I really have 2 different integrals going on there. On this first one, probably u substitution would be a good choice, right? Because I have an x here, and if I do set that equal to u, I would be able to do a u substitution here. On the second one, that kind of looks like arcsine to me. So that's one I'm going to be doing arcsine on that one. So let's set up our first one. So u would be 4 minus x squared, and du would be, what, negative 2x dx. I don't have a negative 2, so I would move that over to the du side. Negative 1/2 du equals x dx. So let's rewrite that integral. I got the negative 1/2, and that x dx goes away, and then I have, so 1 over u to the 1/2 plus, I will just rewrite this du, plus 3 times the integral of 1 over square root of 2 squared minus x squared dx. Okay, so those would be our integrals. Everybody okay with that? Yes? Okay. So let's see, that first one, we have the negative 1/2, and then, you know, we'll think of that as u to the negative 1/2 and just do the reversal power rule. So we have the negative 1/2, and then when I do the reversal power rule, I get 2u to the 1/2. And then what about the arcsine? Is that one of the formulas that needs to be multiplied by 1 over the constant? It is not, is it? So we don't do that. That's the one that isn't, that's not part of the formula. So we don't have to, are not supposed to multiply by 1 over the constant. So that's just going to be 3 arcsine of u over a. So u is x and a is 2. plus c. So cleaning it up a bit, putting the u back in. That gives me a negative. Let's see, my u is, what is that? 4 minus x squared plus 3 arc sine x over 2 plus c. And that's our second one. How's that one? We okay? Yes. You okay? Okay. So we okay so far? All right. Let's go to the third one. This one kind of looks impossible. If I set the denominator equal to u, I don't have another e to the x, so that's a problem. This one would work nicely if we did the whole add a constant, subtract a constant in the numerator. What would happen if let's think about this for a sec, if I add e to the x and subtract e to the x? Let's look and see what that would look like. So if I add e to the x and subtract e to the x, now all of my BC students, I'm hoping, beyond hope, that we understand we can't split the denominator because of the plus, right? Nobody's going to try to split the denominator. Okay, so we're going to split it into two fractions, and my first fraction would be 1 plus e to the x over 1 plus e to the x. That's nice, right? That's just 1. And then minus e to the x over 1 plus e to the x. I could do a u sub now, right? Because I could set the bottom equal to u, and then I would have the e to the x. So let's do that. Let's split it. So I have 1 plus e to the x over 1 plus e to the x minus e to the x over 1 plus e to the x dx. So I'm going to integrate 1 minus, and now let's do a little u sub right here. If we let u equal 1 plus e to the x, then my du, see the derivative of 1 is 0, derivative e to the x is e to the x, e to the x dx. So basically this part right here, the e to the x dx, just turns into du. So we can split it up so it's not that confusing. Let's go ahead and split it. So we have 1 over u du. Is that okay? So we integrate 1 and we get an x. We integrate 1 over u, we get ln u. Now, we know it's ln absolute value of u, so we take a look at what u is. Is it possible for 1 plus e to the x to be negative? It is not possible. So we don't have to put the absolute value bars. In fact, if we do, it's just, if we don't change it to just parentheses, we just haven't finished simplifying. Because if the argument of the natural log is always positive, there's no need for the absolute value bars, and you're supposed to turn them to parentheses. So we would have ln of 1 plus e to the x plus c. Okay, is that good? All right, great. Our last one. Now this one, it's a product. It kind of looks like what we did on Friday, you know, doesn't it? It kind of looks like we might try integration by parts. So it's not going to work, but that's what we would, I think that's what we would try first. So let's go ahead and see what happens. Let's see what happens, and I need a little bit of room up here, so let me erase. All right, so let's try our integration by parts because it's the product of two things. Remember the LIATE? L being logarithm, so I'm going to put this first. So ln of sine x would go first, and then trig, LIATE, the t would come second, so cotangent. Okay, so the derivative of ln sine x would be 1 over sine, and then what? Times the derivative of sine, which is cosine. Okay, what do you notice about this and this? They're the same. They're exactly the same. And we might not even notice that if we hadn't gone and tried to do this. So since a function and its derivative exist in the integral, what technique do we use for that? U substitution. We have to do U substitution here. So we would set U equal to the function, in this case ln sine x. So U equals ln sine x. du would be 1 over sine x times cosine x, which we agreed was cotangent x dx. Okay, so the cotangent x and the dx would become our du, and ln sine x is our u. So we have the integral of u du. Wow, that's much easier than what it was, wasn't it? U du. So, pretty straightforward. 1/2 u squared plus c. So let's put our u back in there. So 1/2, let's see, our u is ln sine x. Now the squared here is to the function, not to the argument. So the squared would be on the argument. On the function, not the argument. Plus c. That means that it's not eligible for like the log rules, when you if it's on the argument, we could pull it in the front. Remember that? But this is not on the argument. It's actually the function itself is squared. So if I rewrote it, it would be ln sine x times ln sine x. It's that squared. It's not ln sine x squared. Does that make sense? Are we okay with that? I really didn't need that extra set of parentheses. I could have just written half ln squared sine x plus c. I didn't need the extra set. This too, or we could write it like this, ln sine x squared plus c. That would be fine. Yeah, we could write it like that too. Any of those would be fine. Okay? We all okay? All right, great. And I don't know how to edit these, so we'll just wing it.